in this example now, we have the circuit shown, the one that we were just analyzing and we found the equation for. We're going to say our capacitor is 15 nanofarads, our inductor is 22 millihenries, and our resistance is 75 ohms. We're going to try and calculate the oscillation frequency of the circuit, how long it takes the amplitude of oscillation to get down to 10%, so almost died out, and what value of R would we have to stick in there to get a critically damped circuit. Okay, let's start with the first part. Calculate the oscillation frequency of the circuit once the capacitor has been charged and the switch is connected to point A. So we start with our switch up here, we move the switch down here, and current starts to flow. So that's what's going on. We know that we're losing some energy to the resistance, so the current is oscillating back and forth between the conductor and the capacitor, the inductor and the capacitor, so it flows one way, then it reverses. As the energy flips back and forth between the electric and magnetic fields. That amount of energy decreases because we lose some energy with the resistor. So we've been through those ideas. The oscillation frequency we're going to calculate is, we know that in these systems, the frequency, the angular frequency of the oscillation, omega primed, is 1 over the square root of LC minus R squared over 4L squared. So we'll put in L equals 22 times 10, why don't we write these down? L equals 22 times 10 to the minus 3 henries. C, the capacitance, is 15 nanofarads times 10 to the minus 9 farads. R is the resistance, 75 ohms. When we put that in our equation, work it through the calculator, we should get, well, I get 55 times 10 to the 3 radians per second. That's the angular frequency. This does ask for frequency. We remember that omega is 2 pi f, so our frequency is going to be omega divided by 2 pi. So this omega over 2 pi gives us 8.76 times 10 to the 3 hertz. So it's got a pretty fast frequency, so it oscillates back and forth really, really rapidly. Part B, how long does it take for the amplitude of oscillation to decay to 10% of its original value? Let's make sure we know what's going on here. So as it oscillates back and forth, so the current flips back and forth, every time it goes through the circuit it loses a little bit of energy, so the charge on that plate decreases over time. The equation for that charge as a function of time was what we came up with in the last video. The charge as a function of time is some initial charge times e to the minus r divided by 2l times t cosine of omega primed. I'm not going to write out that big omega prime thing again, but omega primed is this guy. Omega prime times t plus phi. And that gave us a charge on that plate that looked something like this. So if you were to plot it, that's what it would look like. There's T, there's Q. This outer edge, the envelope, is the amplitude of the oscillation. This amplitude of oscillation is described by this part. So this part gives the oscillation, the up and down in here, the sinusoidal part. This part tells the maximum possible value it can have. So this gives you the maximum you can have. That's the amplitude of the oscillation. So that part is the amplitude. And what we know in our problem is that Q is down to 10% of its original value. So Q is 0.1 of Q0. So let's fill those things in here. 0.1 times Q0 equals Q0 e to the minus r over 2l times t. We see that our Q0's cancel. We've got 0.10 equals e to the minus r over 2l times t. If we want to get rid of our e, we take the natural log of both sides. Solve for our t. T is equal to the natural log of 0.10 over minus r over 2l. Remember that R is 75 ohms. Our inductance L was 22 millihenries. So for the time, for that to get down to 10% of its value, it's 1.35 times 10 to the minus 3 seconds. So it does not take very long to get down to that part. The last part of the question is what value of resistance would we have to stick in there? So we'll take out our 75 ohm resistor and we'll put in a new resistance. What would we have to put in to get a critically damped circuit? Let's remember what critically damped means. So critical damping happens when there's no oscillation. And that was in the intro video. So our regular oscillation looks like this and dies off over time. So that's damped. Our critically damped is it starts at some value and goes right away. So this one is critically damped. So critical damping means no oscillation. What does no oscillation means? Means the frequency of oscillation equals 0. So let's sort that part out. So omega primed is the frequency of oscillation. It's the square root of 1 over LC minus R squared over 4L squared. That's going to be equal to 0. So R squared over 4L squared equals 1 over LC. That's how we get that equal to 0. So that tells us that R squared is 4L squared over LC. One of those L's cancels. R equals 4 times L over C. Take the square root. L is our inductance. That was 22 millihenries. C is our capacitance. That was 15 nanofarads. So the resistance that we'd have to plug in there to get critical damping would have to be 2,420 ohms. So we'd have to put in a fairly big resistor there to get the critical damping, to get rid of that oscillation right away. Okay, one more example and we'll call that good. This one looks like an RLC circuit, but as we read through it, it might not be what it appears right at the very beginning. So in the circuit shown in the figure, switch S1 has been closed for a long enough time so that the current reads a steady 3.5 amps. Suddenly switch 2 is closed and S1 is open at the same time. What is the maximum charge the capacitor is going to receive, and what is the current in the inductor at the time of the maximum charge? So let's get a sketch of what's going on here. Initially, our circuit looks like this. So initially we have our battery, our resistor, our inductor. That switch S1 is closed, has been closed for a long time. Coming over here to the capacitor, that switch is wide open. And what we have in this circuit is that current is flowing, and the current will flow around this way. And that current that flows is 3.5 amps. The other thing the problem doesn't say, but we're going to assume is true, we're going to assume that the capacitor is uncharged. So that's what's going on right at the beginning. And then of course there's not going to be any potential across the ends of the inductor because it's been closed for a long time and that current is steady. So then at t equals 0, what happens is the two switches flip, or they toggle, I suppose, if you like that language better. So this one opens, we've got our inductor there, we've got our resistor there, and now this one closes, so now our capacitor is in the circuit. So what's going on right here in this one is that the inductor has a current of 3.5 amps running through it. When this switch is opened, this branch is no longer part of the circuit. This inductor has a current of 3.5 amps, and it will eventually start to change as the capacitor starts to charge up, but it won't charge immediately because it's an inductor that opposes the change. So right here at this point, the current in the inductor initially is 3.50 amps. If this is the initial current, and the charge on the capacitor initially equals 0 because we started with an uncharged capacitor, so these are things at t equals 0. So if the current here is 3.5 amps and the charge here is 0, that means this must be the maximum current, because there's nowhere else for current to come from. Okay, so there's our setup. We haven't started to work on the problem yet, but now we know what's going on. So let's think about conservation of energy. If we've got a maximum current right here, we have the maximum energy stored in the magnetic field. In order to get maximum charge on the capacitor, we'd have to have maximum energy stored in the capacitor. So the maximum energy here would equal to the maximum energy here. They don't happen at the same time, of course. Over time, all the energy out of this field transfers into the energy in this field. So our conservation of energy states that total energy is conserved. So initially at t equals 0, all of the energy is in the inductor, and that's a maximum. And then sometime later, you might remember from Monday's class, it would be a quarter of a period later. We're not asking what that time is now, but that's something certainly that could be asked. So at time equals 0, all of the energy is here. At a different time, all of the energy would be here, and that's when the capacitor would have maximum potential energy. Let's fill in what both of those energies are equal to. For the inductor, it's a half times L times the maximum current squared. And for the capacitor, it's 1/2 times the maximum charge squared divided by the capacitance. So we can solve for the capacitance. Those 1/2s cancel. So Q squared is going to be C times L, C times L times I squared. That's Q squared. To get Q, we take the square root of the whole shebang. So our capacitance C is 5 microfarads. Our inductance L is 2 millihenries. And our maximum current is the current we had right at the beginning, 3.5 amps. That gives us a maximum charge of 3.5 times 10 to the minus 4 coulombs. So that's the most amount of charge we can get on that capacitor, and that happens when all of the energy gets transferred into the electric field of the capacitor. Part B, what's the current in the inductor when the capacitor is at its maximum charge? So part B, I don't have quite enough space up there. So when the charge on the capacitor equals the maximum charge, well, what happens then is all of the energy is stored in this field. None of the energy is stored in this field. So the energy here, 1/2 times L times I squared, would have to be 0. That means that the current in that capacitor, or in that inductor, is 0. So all energy is in the capacitor, which means no energy is in the inductor. Since energy is 1/2 Li squared, I must be 0. Okay, so that clues up those couple of examples. They're not that in-depth, but we didn't have a lot of time at it. So I think last I would say is just thank you for hanging in there. I think this has been a real trial of a term, and it was a pleasure to have you. I wish it could have turned out to be the semester I had wanted and we had gotten the full course in. Hopefully you've managed to muddle through okay. I'll have details of the final exam out in the next few hours. What else? Term test 3 grades will be up in the next hour. As always, I'm here. Please reach out with any questions or concerns, and we'll try and address them the best I can. Anyway, you were a super class, and thank you for being part of it.